Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
I have the privilege of delivering a couple of presentations on the Back to Basics track this year, and as you probably know, each session in the track is about a single concrete topic, like this one, which is about C++ templates. Our goal with the Back to Basics track is to produce content that covers important things you need to know to be a working C++ programmer in today's world. Many thanks to our Back to Basics track chair, Arthur O'Dwyer, for putting together the track program, and to our conference chair, John Kaub, for making all this happen. So it's a pretty straightforward presentation. I'm going to talk a little bit about why we have templates. I'm then going to spend some time talking about template fundamentals. And I'm going to talk about various categories of templates in more detail. And that part, the categories in detail, is probably going to be most of what will be in part 2. Some of it might make it into part 1 today. It's actually intended to be one continuous presentation rather than divided into 2 separate parts. So I also want to set expectations about what the level of content is going to be. Back to Basics is intended to be C++ 101. So the level of sophistication of this talk is going to be as if I was talking to someone who has some experience with C++ and may have used templates a little bit, but doesn't really understand them very well, or has never written a template, or perhaps is even new to the language. If you were taking, Computer Science 201 and it happened to be taught your first exposure to C++, and there was part of the course or an overview of part of the course having to do with templates, that's the level that I'm aiming for. If you're a very sophisticated template user, you probably know everything I'm going to say. If you've used templates for a while and you know a bit, hopefully I can fill in some gaps. If you haven't used them at all, hopefully this will be a nice introduction for you. So what I'd like to do is cover some of the major features of templates and explain some important terminology and concepts and sort of point to next steps for where you can go beyond this. There are several references that I use all the time when I'm working with templates. First, foremost, is Templates, the Complete Guide, 2nd edition. David van der Voorde's, Nico Jasutis, and Doug Greger's book, published. It's the 2nd edition from 2018. You should consider this to be the Bible of templates, including everything up through C++ and including C++ 17, and a good part of C++ 20 is covered in it, even though 20 hadn't been published at that time. I also like Effective Modern C++, Scott Meyer's book. Even though the last edition was published in 2015, and it only covers C++ 14, there are discussions of certain topics in there that I don't think you'll find a better explanation of anywhere. Template argument deduction, perfect forwarding, R-value references. Scott covers those things in a very clear, a very lucid way. I highly recommend that book. Bjarne's book, of course, is a great book. It covers lots of things everywhere throughout the book. And finally, CppReference.com. I have that website open continuously. I use it so much that I feel guilty about not actually contributing money to it. Maybe I should. All right, so let's start with the following questions. What are templates and why do we have them in the language? Well, the answer is because we want to be able to reuse code. So let's look at some bad old days. Let's say that we're writing in very primitive C++ or C++ before templates, and we do have function overloading in this slide. So we've got a function called min. We want min for ints. Pretty straightforward function to write. It's trivial, we know how to do it. If we want it for doubles, we can do the same thing for doubles. It's effectively the same code. And if we happen to have strings or primitive strings in this version of the language that I'm thinking of, then we can do that for strings as well. But the problem is, there's a lot of cut and paste there, and it's easy for errors to creep in. Let's go back even a step further to the days of C, and this is actually very similar to code that I wrote many years ago before I learned C++ and I was working in C. Suppose I need to implement a singly linked list, right? And I need to contain integers. Well, I might have an int node that is defined like this, where I've got a pointer to the next node, and I've an integer, which is the value that that node holds. Then I've got a structure, int list, which is the thing that represents an int class. I have some member functions for appending nodes onto the list, for prepending nodes onto the list, and for clearing the list. Makes sense, it's easy to do one time. What if I need it for doubles? Well, again, I have to cut and paste the code. And so, since I've already said I'm working in C, I also have to make up new names for everything. New names for the nodes, new names for the functions. So, again, with cut and paste, there's a lot of opportunity for error to creep in. Another approach that people have taken in the past is with type erasure. If you've ever done any work with Linux, this is usually part of libc, and it might be part of the libc runtime with Windows. But I work on Linux a lot, and this is a function that's available on every Unix I've ever worked on, called qsort, and it does a quick sort. And so what we've got here is we've got a pointer to some data. We have a thing that tells us how many data members there are in this array. And we have another parameter that tells us the size of each parameter. And then we have a pointer to a function, a comparator. And that comparator's, it takes two void pointers and it returns an int. It's very similar to strcomp. The int is -1 if the left argument is less than the right argument. It's equal to 0 if the two arguments are equal. And it's greater than 1 if the left argument is greater than the right argument. And to use it, I might write a comparator for doubles that looks like this. And so there's type erasure involved here. I get pointers to my two things that are supposed to be doubles. I then cast them to double pointers and I dereference them to get the values of the doubles themselves so that I can actually do the comparison here and return a sensical value. When I want to use that in a function, well, so here's an array of data, some of my favorite constants. And to call qsort, I would pass it a pointer to the data, the number of elements, the size of the doubles, and a pointer to the comparator function, right? That will work. That will give me the right answer. Well, let's suppose I want to do it for character arrays, right? Well, I could write another comparator like this, takes void pointers, casts them to const pointers, and passes them directly to strcomp. And I've given it a different name, so there are no name conflicts. And there again, I go and I pass it into the function and I use it, right? I pass in there's my string data, I pass it in, I've got everything right, and it fails. Boom, because I passed in a pointer to the wrong comparator. All the comparators have the same type, and it was very easy for me to make this mistake. And this is one of those silent things that may or may not fail and cause crashes that are hard to track down. Another approach that people took was reusing code that used macros. And I've actually done something like this 30 years ago. You have a macro that generates a type for you, like templates might have done. And then you invoke the macro to actually, quote, instantiate the types, but actually define the types, and then call them. Of course, you have to know what the names are, and there's always the opportunity for the same sort of mistake. Here I've created comparators, a float and double, but I'm using them incorrectly here. I'm using a double character with float data. That's a recipe for problems. So these problems centering around code reuse have been around for a very long time, since after the dawn of computing. People started thinking about it in the late 50s and the 60s. In the 1970s, there were some languages that began allowing algorithms to be written in terms of types to be specified later. And then these algorithms, and remember this is the 70s, object-oriented programming hadn't caught on yet. People were still thinking in terms of data and functions. Procedural programming. Algorithms, the functions, were then instantiated using type arguments that were supplied sometime after the definition of the function itself. There wasn't really a name for it then, but it came to be known as generic programming. And as far as I can tell, and based on my research, and I could be wrong, generic programming as a term was first coined by Alex Stepanov and Dave Musser in a paper published copyrighted 1988, published 1989. And here's the quote from one of the first sentences in the paper. Generic programming centers around the idea of abstracting from concrete, efficient algorithms to obtain generic algorithms that can be combined with different data representations to produce a wide variety of useful software. Well, that kind of describes what we want to do. It's a little bit of a mouthful. A few years later, Bjarne, writing about the origin of generic programming in 2007, has this quote, and I'm not going to read the whole thing to you, but I've bolded the part that I think is the most concise and elegant statement of generic programming that I think I've seen anywhere, and that is, lift algorithms and data structures from concrete examples to their most general and abstract form. And this pretty much jives with Stepanov's original conception. You look at a bunch of concrete examples of an algorithm and how it works and what the differences are from example to example, and then from that, you create a more abstract representation of the algorithm that encompasses most or not, if not all, of the differences in the concrete examples that you looked at. And hopefully then that abstract algorithm can then be later rewritten or instantiated, if you will, in order to generate the versions of the concrete algorithms that you used as the basis of the abstraction. So, in C++, we support the idea of generic programming with templates, right? So, let's talk briefly about some template categories. And this is a very quick overview of the kind of templates that you're likely to have seen at some point, right? We have function templates. And function templates are recipes for making functions. So, here's an example of 3 different function templates. Here I've got a simple implementation of a min function template, and this is actually a definition of min. Then I've got some declarations of swap and declarations of sort. And these are not exactly, but they're pretty close to what you would find in the standard template library. I actually cut out some of the extraneous const exprs and other things that visual noise that obscure the point that I'm trying to make. And that is these prototypes, these declarations, these definitions specify a recipe for going from a set of template parameters to actual concrete code. We also have class templates, and class templates and function templates were actually came from the original implementation of templates beginning around the 1988, 1989 timeframe. And class templates are recipes for making classes. And again, taking some inspiration from the standard template library, here are some examples of class templates. Here we've got array, which creates a fixed size array having n elements of some type T. We've got vector, which is the go-to container class for just about everything. And map, which you can use to create a dictionary, if you will, or an associative array. There's also member function templates. They were also part of the original C++ 98 standard. They were added a little bit later after function templates and class templates. And these are recipes for making member functions of classes. And I'm calling them out as being distinct from function templates, even though they obey almost all of the same rules, because the lookup rules for function templates and the lookup rules for member function templates are different. But the rules governing type deduction of parameters, those are all the same. So here's an example of a member function template that comes right out of the standard library and is part of vector. And it's the insert member function. Here, I've got vector, which is parametrized on terms of the element type, and some allocator, which allocates the memory for it dynamically. I've got these nested type aliases, iterator and const iterator, which are defined by vector, and here I've just left them empty. And then I've got the insert member function, which is parameterized in terms of some other unknown type called input iterator. And what insert does is it takes a const iterator to some position in the vector, and const iterator is a vector iterator. And then it takes two other input iterators, first and last, that describe the range of some other sequence, which is completely unrelated to vector. And then insert iterates over those input iterators from first to last and inserts the elements at the position pointed to by pause. New in C++11, we have alias templates. And these are recipes that allow us to make type aliases, and they're incredibly useful. Here's just a sampling of what you can do with it. And really, I find them most useful for, in a sense, being binders on types. So here we've got SA vector for my special allocator. So here I've got a vector, and what I want to do is I've created this type alias SA vector in terms of vector T and my special allocator. And I can invoke SA vector with just the name of the element, and the type alias fills in the rest for me. And so SA vector is actually that type, vector of float of my special allocator of float. Likewise, we can, if we wanted to have a map where we sorted our keys in descending order instead of ascending order, well, then I could pass a comparator called greater, which sorts keys from greater to lesser, and I could create this nice type alias that gets rid of all the ugly parameters for me so that I can just have a nice clean instantiation like this. And so my map is a map where the keys are sorted in reverse alphabetical order, and MSI is an instance of that map. And finally, I've got a much more complex thing, which is from a linear algebra proposal that I've prepared for standardization. And here it's got a lot more template parameters. It's a lot more complicated. I've got these, the element type, the number of columns, an allocator, customization traits types, which have default parameters. And I'm creating this alias called general row vector. And general row vector is an alias for a basic matrix that uses a matrix storage engine of this element type that has extents 1C, which means one row and C columns. It has the allocator A, and it has a matrix layout of row major, and it uses these customization traits. And now I can just create a general row vector using these two, using the type and the number of elements, and I don't have to type out all of the rest of this stuff. It's incredibly useful. It's a way of binding template parameters. We also have variable templates, which were introduced in C++14, and these are recipes for making variables or static data members. And so this is sort of the canonical example. I want to be able to represent pi in a number of different formats. Perhaps I want float, double, long double, or some other thing. So as long as that thing has the ability to be constructed from a long double literal, then I can create this this static type, or this static variable, which I call pi, and then I can use that variable pi as if it is const expr or variable or is at a literal, and so that value of pi is actually known at compile time. So if I did pi of float at compile time, I would have the value of pi with a float representation, and likewise for double or long double. And so I can do things like this. In this computation, pi of t is actually treated, in a sense, as a compile time constant. Actually, it is a compile time constant. Likewise, here's an example of something, if you are familiar with what type traits are. We have a type trait in the standard library called isArithmetic. And given a type isArithmetic, it defines a nested value, a nested Boolean value that's either true or false. And that nested value is true if type t is a Boolean, is true, or is an arithmetic type, and value is false if t is not an arithmetic type. And so what I'm doing here is I'm creating compile time variable called isArithmeticV that's parameterized in terms of some type t. So how would I use that? Well, here I've got a function where I'm going to initialize an array of raw data. So I've got a pointer to some stuff, and I think that, and I've got enough space there for n elements. And this is very similar to the way that std allocator might initialize something. So what I can do is I can, at compile time, check whether t is an arithmetic type. And if it is, I'm just going to mem copy 0 into that arithmetic type, and everything is initialized and zeroed very quickly. Fastest possible way you can do it. Otherwise, if it's not an arithmetic type, then I'm going to call a standard library function called initializedFill, which is going to take a default constructed value of t, and it's going to copy construct it into each location. And the nice thing here about if const expr is because isArithmetic t is a compile time, returns a compile time constant, this decision is made at compile time. And if this construct is true, then only this code is generated. If this construct is false at compile time, then only this code is generated. And at runtime, there is no branch. At runtime, the code path that is taken has already been determined at compile time. Make sense? It's very cool. Finally, in C++20, we have Lambda templates, which are recipes for making lambdas. This is my only slide about them. They're still very new. And honestly, I don't fully understand them yet or all the use cases. But what they do allow you to do is explicitly parameterize lambdas with template parameters. And they provide for generic lambdas like the older style C++14 generic lambdas to take auto parameters do. And I've just got a very simple example here of how one might instantiate one and use one. Okay, so you probably haven't seen any Lambda templates, but you've probably seen, almost certainly seen function and class templates, probably member function templates. Alias templates and variable templates are still relatively new. Maybe you've seen them, maybe you haven't. So let's move into important stuff, fundamentals. Now, one of the things I wanted to do with these two talks was to, instead of trying to cover a wide range of topics in very shallow depth, I wanted to cover a smaller selection of topics in greater depth. And in the interest of full disclosure, I'm not a compiler writer, and I'm certainly not a language lawyer. I am a heavy template user. I'm not sure I'd consider myself an expert on templates, but I've used them for a very long time. And what I'm trying to do is impart in these two sessions the things I wish somebody had told me when I was learning about templates in order to save you time. Probably 99% of you that are watching this are not going to be compiler writers or language lawyers, but you are going to want to use templates. And what I'm hoping to do is provide you with some basic fundamental knowledge about underlying ideas that will help you understand templates better, especially when other people are discussing them or you're reading about them. And so I'm going to spend time discussing some terms and the concepts underneath them and what they mean. And I think it's very important, and I hope maybe you won't appreciate it now, hopefully you'll appreciate it later. So let's talk about terminology. If you want to discuss templates with any sort of clarity, that means you have to use the terminology with precision. So, for example, how do we refer to templates that we use to generate classes? Well, classes and structs and unions are what we normally refer to as class types, and that's a term that's used in the standard. The standard also uses the term class template in a very specific way to mean a parametrized description of a family of related classes. A class template is not a class. A class template is a parametrized description of a family of related classes. The C++ standard also provides us with parametrized descriptions of the other things that I mentioned before. Functions, member functions, type aliases, variables, and lambdas. And you can take any of those 5 terms and sort of substitute them in the sentence above that, and you get the idea. So I'm a little nitpicky about this. The standard treats the term this thing template consistently. Template is the noun indicating a parametrized description, and thing is an adjective specifying the family of things to be parametrized. So I've got a little table here expressing my pet peeve. If you've got this kind of template on the left, that's the parametrized description of things that it describes on the right. And it's important. The order is important. The adjective and the verb is important. Walter Brown actually had a great talk a couple of years ago where he also mentions this point. And he says, think about it. Milk chocolate is an entirely different thing from chocolate milk. And that's his quote. Thank you, Walter. So the only thing that's really important to talk about templates in this context is thing template, class template, function template, variable template, Lambda template. And also, another pet peeve of mine, the associated verb is to parametrize or parameterize a class, not templatize. Templatize is not a verb. If you say that to me, I will likely vomit. So parametrize, it's a word that's been around, it's been part of mathematics for decades, it's in the dictionary. Templatize is not. All right, I'm going to talk about now some non-C++ definitions that are important, non-template definitions that are important to understand templates. So translation units. The standard, we build software, we compile software, and compilation is the process of converting source code into binary object files. From a high-level perspective, we've got the 4 stages of compilation which you see before you: lexical, syntactic, semantic analysis, code generation. And in C++, we typically generate 1 object file for each source file. Linking is the process of combining object files and binary libraries to make a working program. We're all familiar with this. The standard calls the process of compilation translation. And in C++, translation is performed in 9 very well-defined stages. You can read about them in the standard. Phases 1 through 6 do lexical analysis. And these are what we usually think of as being called pre-processing. The preprocessor is responsible for these stages. And the output of phase 6 is called a translation unit. And that translation unit, in very general terms, is defined in the following way. It consists of a source code file, plus all of the headers and source files that have been included into the target source file via include directives, minus all the lines that have been skipped by if-defing them out, and having all macros expanded. Phases 7 and 8 perform syntax analysis, semantic analysis, and code gen, and these are what we usually refer to as compilation. This is what the compiler proper does. Templates are parsed in phase 7, and templates are instantiated in phase 8. And the output of phase 8 is called a translated translation unit. You've translated the source code from the original translation unit into some other representation. So it's a translated translation unit. Phase 9 performs image creation, which is what we usually think of linking, and the output is an executable image. So if we look at a sample translation unit for fun, here on the left, we've got a very simple header file where I've defined a function, I've included IOStream, I've got a source code file, hello, where I've included the header and the source, and I've got my main. So compilers provide a way to inspect the contents of the translation unit, or something very close to it. And with GCC, you can use the -e flag, and here I've given the commands that print what comes out of the preprocessor. And interestingly enough, there are quite a number of lines of code in there in main.i and hello.i, as you can imagine. And there's the count, at least with GCC 10.2 on Ubuntu 8.04, right? And you can see the difference is 1 line between the 2 translation units. And the reason is there's 1 line difference between hello.cpp and main.cpp. So, declarations and definitions. Moving on to the next important thing. An entity is one of these things. The standard defines an entity as being one of these things. I'm not going to read the entire list to you. I did highlight the things that are important for this discussion, templates and template specializations. Entities are important because entities are things that we give names to in our programs. And a name is an identifier that denotes that entity or label. Every name that denotes an entity is introduced by a declaration. Conversely, or saying it another way, a declaration is a construct, a syntactic construct that introduces one or more names into a translation unit. A declaration can also reintroduce a name into a translation unit as long as the reintroduction of that name is identical to the previous introductions of that name. A definition is a declaration that fully defines the entity that's being introduced. A variable is an entity that's been introduced by the declaration of an object or a reference other than a non-static data member. I'm not going to worry about that. So every declaration is also a definition unless certain things hold. I'm not going to read the entire list to you, but of most importance here, a function declaration without a corresponding definition of the body, a declaration of a class name without a corresponding definition of the class body, or a template parameter. Those are the three things that are of most interest to us here. The set of definitions is therefore a proper subset of the set of declarations. And so I've got some quick examples here. Declarations on the left, my big Venn diagrams, declarations on the left, definitions on the right. I've got declarations of some external definitions of some global constants. I've got definitions on the right. Here I have a declaration of a function f. I've got the definition of that same function on the right. I've got a declaration of a class, a non-template class called foo on the left. I've got a definition on the right. I've got a namespace declaration, a namespace using declaration on the left, and a namespace definition on the right. I've got a declaration of a struct called bar on the left, and I've got the definition of its member function compute on the right. I've also got some declarations on the left of a type alias, bar vec, and I've also got a type alias for the primitive int type where I've capitalized it. There are no corresponding definitions for those because those are type aliases, and the declaration, there is no definition of a type alias. The declaration is the thing. So let's look at some template declarations and definitions now that we know what they are. So here I've got at the top a declaration of a function template max. There's no body at the top, that's a declaration. Below it, I've got the definition. Here I've got a declaration of a class template pair, very similar to the pair in the standard library. It's a declaration only because there's no class body. Next, I've got a definition of pair. And I can actually have that declaration and that definition in the same translation unit. My declaration of pair is a reintroduction of the name pair, and that reintroduction of the name has the same signature, if you will, the same type signature as the original declaration. I can have a member function declaration. So here's my declaration of my member function template called insert from my previous example. And here is a definition of that member function, which I've done outside the class definition. So I've got a class definition. So this whole thing is a class definition. It has a member function declaration, and that member function has its definition outside the class definition. I can also define my member functions right inside the class, as I've done here. Rather than doing it out of line, I'm doing an inline definition of insert here, and I'm not going to repeat that code. I've also got some declarations, a couple of other declarations, a declaration of an alias template called myMap from the previous example, and also from the previous example, the declaration of the variable template called pi. All right, so we know what a translation unit is. We know what declarations and definitions are. We have some feeling, intuition for what the difference is between them. Let's talk about the one definition rule. A given translation unit can contain at most one definition of any of these things. And here, talking about templates or default template arguments. There can be multiple definitions, but there can be multiple declarations, but only one definition. So it's important to remember a program has to contain exactly one definition of every non-inline variable or function that's used in the program. You can have multiple declarations of a non-inline thing, but you can only have one definition. For an inline variable or an inline function, you need a definition in every translation unit that uses it. Inline was originally a suggested optimization made to the compiler, but it's now evolved to mean multiple definitions are permitted. Exactly one definition of a class has to appear in every translation unit that needs a definition for the class. And the rules for inline variables and functions also apply to templates. That's why you can have a template declaration that's fully written out in a header and included in multiple places, because the compiler treats template definitions as though they're inline. So my simple guidelines for observing ODR keep you out of trouble most of the time. If it's an inline thing that gets used, make sure you define it at least once somewhere. If it's a non-inline thing, make sure it gets defined at least once in every translation unit that uses it. If it's a non-inline, non-template thing, make sure it gets defined exactly once across all translation units. If it's a template thing, define it in a header file, include the header file where the thing is needed, and let the tool chain, the compiler, and the linker sort out the rest. Except in rare circumstances where you might need finer control. So let's talk about template parameters and template arguments. Here I've got a class template pair and a function template max. And so template parameters are the names of the things that come after the template keyword in the declaration. On the right, I'm actually using those declarations, and I'm instantiating some code. And so template arguments are the concrete things that are substituted for template parameters in order to create template specializations. So template parameters come in three flavors. They have type parameters, they have non-type template parameters, or NTTPs, they have template parameters, which are actually using templates as a kind of parameter. As you would expect, type parameters are the most common, and they're declared using the class or type name keywords. And in this context, the keyword class or type name is interchangeable. These two declarations of pair are identical. These two declarations of max are identical. So template parameters don't necessarily have to be types. Template parameters can be things that are determined at compile time, like we saw already in array. On the left, I have a class template array, which uses a compile time constant n to size the number of elements. On the right, I've got a silly function that I wrote that always increments some integer by a constant amount. So non-type template parameters represent constant values that must be determined at compile time or link time. And in order for that to happen, their types have to be an integer or a numeration type, int, long int, long int, unsigned int, or an enumeration type, a pointer or a pointer to member type, stood null pointer t, and some other things that are sort of corner cases. Another kind of parameter that can be used is template parameters. So template parameters themselves can be templates. And remember that these are placeholders for class or alias templates. They're declared like class templates in the template parameter list, but they only use the class and type name keywords. And so here's an example of an adapter that I've written. What I want to do is I want to have some sort of adapter that sort of emulates a stack. And I want this thing to hold some element type, but I also want to be able to specify at compile time what kind of container I'm using. C. So this business right here, this is a template parameter. So class C is a template that uses these parameters. And so then in my class definition, I use this template, C, and I parameterize C in terms of my element type T. And then what I do is I have my member function pushback where I take a T and I push it onto the back of my data structure. I don't know what my data structure is until I instantiate it. So here I've instantiated a couple of adapters. Here I want an adapter which contains ints, and I want the representation to be stood vector. Stood vector is the name of a template, and so it gets substituted in there. I have another adapter where I want to have a stack of longs, and I want to use stood list for that. And it's a very powerful paradigm because I can determine the representation, not only the parameter types, but internal representation at compile time. It's kind of like using a function pointer. Template parameters can have default arguments. So we've already seen some examples of that with the default argument for vector, the allocator type. I could create my own array type where the default number of elements is 32 for some reason. In my adapter class that I just showed you, I could have a default representation type of vector. And so when I when I instantiate them and take advantage of the default parameters, I get the actual instantiations that you might expect. For class and alias and variable templates, the default parameters have to be at the end of the parameter list, very much like with function parameters. So this works because after T0, all of my parameters have default values. But this is an error because I have one at the end for this class template that is non-default. Function templates, surprisingly, don't have this requirement. Template type deduction that functions do can determine the template parameters. They determine the template parameters in a different way. So here's an example from JUCE, Van der Voort and JUCE, where I've got a template called address of, and what I want to do is I want to take a reference to some type and return a pointer to it. And I'm going to cast that pointer to some other type, RT, and my default is void. So I take the address of the value, I cast it to RT, and I return that pointer. And if I don't explicitly specify RT when I call this function, by default, I will be casting to a void pointer. So let's go back and look at template parameters and template arguments again, because I want to get to specializations, which is really very important. Template parameters are the names that come after the template keyword, and template arguments are the concrete items that are substituted for template parameters to create a specialization. So I've got, another way of looking at it is I've got my template, which is a recipe. It's not a thing, it's a recipe to make a thing. And I've got my specializations. And my specializations are the things. They're the things that do stuff for me at runtime. So the concrete entity that you get, that the compiler generates when it substitutes template arguments for template parameters, is a specialization. And specialization is an entity, and it's an entity that has a name, and it has this syntactic form that I've just shown you. And if you ever hear people talking about template IDs, that's what they mean. A template ID is the name of a specialization. So from our earlier example, we've got pair as a class template and max as a function template in the code on the right. But when we actually use instances of these, pair, string, and double, max of double, and max and string are the names of the specializations that have been created by the compiler. So how do we get from template to specialization, right? We've got templates. Templates are recipes. They're not things. They're recipes to make things. We want to get to specializations, which are the things that do work for us, the stuff we get paid for. Well, the template is a recipe that tells how to generate something useful. A specialization is the useful thing that gets built from the recipe. So how do we get there? There's two ways that we get there: through through a process called instantiation, and also through a process called explicit specialization. So at some point, we want to use the recipe and make a thing. Most of the time, the compiler knows how to cook the recipe for us. Now, at various times through the process, the compiler takes concrete parameters, arguments, and substitutes them for the template parameters. Sometimes it's only a tentative substitution, like when it's doing type checking for overload resolution. It will plug in some types and see, and just tentatively say, does this combination of template arguments match this member of the overload resolution set? No, well, I'll try the next one. And there's no error there because it's looking for matches. It's not actually trying to lay down code. Sometimes the result of substitution is actually to lay down code and create a specialization. So template instantiation is the process. It's a process that occurs when the compiler substitutes template arguments for parameters, and it generates a specialization for you. The specialization that results is informally called an instantiated class. Likewise, for the other template categories, you have instantiated function, instantiated member function. Those are informal names. People also refer those instantiations. So now we have this unfortunate circumstance in our business where the term instantiation is overloaded, and you have to be very careful about the context. Instantiation, more properly template instantiation, is a noun that's the name of a process that the compiler goes through. People also informally use the term instantiation to mean the specialization that the compiler has generated for me. So instantiation can be by the compiler in two possible ways: implicitly and explicitly. So what are the relationships between instantiation and specialization? And this is, to me, some of the most important parts of the talk, and I'm probably going to run a little bit late, but please bear with me. So I'm going to borrow a diagram from Dan Sachs in a talk he did 2 years ago, and I'm not going to show you the whole diagram at once. I'm going to build it piecemeal. But when I saw this and finally understood what Dan was saying, it was a bit of a revelation to me. So if you're a little bit familiar with UML, the arrow means is a. So we've got specialization. It's a thing that we want to make. It's the result of a recipe being cooked, right? The compiler will make an instantiation. An instantiation is a specialization that's been made by the compiler. So an instantiation is a specialization. So we have implicit and explicit instantiation. So in general, when the compiler is going through code and it sees the use of a specialization, in other words, it sees, the name of a template that's got some actual concrete parameters substituted in for it, then it tries to create that specialization by substituting the template parameters, the template arguments in the code for the parameters in the template. This process is totally automatic behind the scenes. You don't see it most of the time except for the errors that it generates, right? And this is called implicit on-demand or automatic instantiation. You'll see these terms in JUCE and other places used equivalently. And really, what we're saying here is that the compiler is making the decision. The compiler sees the usage of a template, and it's making the decision about where, when, and how much of the specialization it needs to create. In other words, how much of the recipe do I have to cook to make the thing that gets used? So in this little quick example, again, these are cases where automatic instantiation or implicit instantiation is done. I've used the name of a template with explicit template parameters here. I've used the name of a function template with an explicit parameter here. And here I've used a function template where the compiler, based on the arguments, has deduced what the arguments should be. So templates. Implicit instantiation doesn't necessarily instantiate all the members of the class. The compiler, if you have a class like standard library containers that have no virtual components, no virtual functions, there's no vtable to be instantiated, then the compiler will basically only generate the minimum number of functions it needs to do the work that you've asked it to do. So consider this function, f, where I've instantiated a vector that has two elements, 1 and 2. Well, only two things, well, of course, there's going to be some private implementation. So the only things that are going to be instantiated are this constructor, the private implementation that's necessary to carry out the constructor, and the destructor. Append, indexing, insert, erase, none of that stuff is going to be generated. Only the stuff that's actually needed to run F is going to be instantiated. So if we go back to our diagram, we now have one kind of instantiation, which is an implicit instantiation. An implicit instantiation is one that's performed for you automatically by the compiler when it sees the usage of a template. And an instantiation is a kind of specialization. We also have the ability to create explicit instantiations. Sometimes we want to tell the compiler where and when exactly we want an instantiation to occur. And so the process for doing that is called explicit instantiation. Perhaps we have some big, crazy template that takes forever to compile, and what we want to do is we want to instantiate all the code in one translation unit, and because it takes minutes to compile, and we just want to use references to it in other translation units, and that's sufficient for our needs. So we can have an explicit instantiation request, and it looks like this. And what you do is it looks very similar to a template declaration, except you've taken the parameter list inside the angle brackets away from the template, you've moved them after the type name, and you've filled in the actual template parameters that you want. And so all of these lines of code that you see here, these are all explicit instantiations that create definitions, specializations of these things. Now, unlike implicit instantiation, an explicit instantiation of a class template instantiates all the members. When you tell the compiler, hey, I want you to do an explicit instantiation of vector of foo, the compiler doesn't know, well, I just want, append or insert. It just goes and it does everything. Now, you do have a little bit of control over that. You don't have to necessarily instantiate the whole class. You can explicitly instantiate individual member functions. And so the syntax for that looks sort of like this. I begin with the template keyword and then fill in the function signature, except here with vector, I filled in the actual parameters for which I want pushback instantiated. I never actually had to do that in any production code. I find it useful as a debugging technique sometimes. Just throw in an explicit instantiation and see if the compiler likes it. So when you're doing explicit instantiation, you run the risk of violating the one definition rule. So if you explicitly instantiate a template somewhere in one translation unit, you have to make sure that you don't explicitly instantiate it somewhere else. So you don't want to do your explicit instantiations in headers. But if you do your explicit instantiations in source files, how can you create a header that lets other translation units know where to find the definitions, right? Well, there's syntax for that as well. So let's go back and look at our explicit instantiations, and we're going to put those in source code file foo. So these instantiation requests, these explicit instantiations are going in this translation unit that's created by foo.cpp. But for other translation units to be able to take advantage of it, I can create a header called foo.h, and then what I can do is if I put the keyword extern in front of those, now I've created declarations, not definitions. So I can include foo.h anywhere that I need those things, or my foo.h anywhere that I need those things, and the compiler will see that and say, okay, well, these are extern templates. You've guaranteed that these are going to be defined somewhere else. I am not going to define them. I'm not going to do implicit instantiation. I'm going to trust that you have made sure that they are defined somewhere else so that when the program is built and the linker runs, everything is found. So going back to our diagram, explicit instantiation is another kind of instantiation. So implicit and explicit instantiations are kinds of instantiation. Instantiation is the cooking of the recipe, the creating of the specialization by the compiler.
We have a question online.
Oh, sure.
What would be some real-world uses for explicit instantiation?
So a real-world use of explicit instantiation is if, for performance reasons, I have a template that's very expensive to instantiate. Maybe I've got a translation unit where I've included millions of lines of header and I have very complicated template stuff going in there, and to compile that and generate object code takes minutes. It's a common situation. Well, perhaps I don't want to necessarily pay that cost for every translation unit. So for the things that are expensive, I might explicitly instantiate them inside the translation unit and use extern declarations in other translation units so they don't have to pay that compilation cost. Another use case, which is probably actually more common, is the case of shared libraries or DLLs. I want to instantiate something and I want to put that instantiation inside the DLL, but I want clients of the DLL not to do the instantiation. I want them to use the instantiations that are in the DLL. So I instantiate the templates in the DLL, and for header files for things that link to the DLL, they see the external declarations. So that's the use case. So we've talked about the compiler creating specializations, but what if you want to customize the behavior of a template for a special situation, right? We call this explicit specialization. So here, I've got my min template again, but what happens if I want to compare raw character strings, traditional pointers to character const arrays? And so I call min, right? Min will compile, I will get an answer. You can debate whether or not this is undefined behavior, but whatever answer you get, it's incredibly likely to be the wrong answer. So there are situations where min works a lot of the time, but not all the time. But I still want to use min as a template. I want it to do the right thing. So we can use something called explicit specialization, which is a user-provided implementation of a template that has all the template parameters fully substituted and all the parts of the template are fully defined. So, whoops, I didn't mean to do that. So in this case, I've got my primary template min, but now I'm creating an explicit specialization. So my explicit specialization begins with template with empty brackets, and then I'm going to return a const pointer. I'm going to take my two const pointers. So this pattern is very similar to the pattern that you see up here. And instead of doing, ternary comparison, I'm going to call strcomp, and I'm going to return the result for that. And now I'm going to use that, and when I call min, the compiler is going to look at those parameters, and it's going to say, well, I've got these two templates. I've got this explicit specialization. This explicit specialization is a better match for the parameters than the primary template. I'm going to use this one, and then you'll get the right result. So it's probably more common to use explicit specialization with class templates. And so say you wanted to do something with maps. So you might create your own comparator. So here is you might create a myless, which is very similar to that defined by the standards, your primary template. And then if you need to store character strings in your map, the full specialization. And you could use it in map in this way. The thing to remember is an explicit specialization is only valid syntax if the primary template has already been declared before it. If I tried to declare my explicit specialization of myless before I declared the primary template, that would be a syntax error. So, rounding out the diagram, and I'm out of time, so I'm gonna break here and pick up at this point when we meet again on Friday. Rounding out the diagram, all of the relationships between instantiation and specialization. So, a specialization is a thing. It's a thing that's made from a template. It's a useful thing that runs at runtime. There's two ways to make that thing. There's instantiation, which you can also think of as being implicit specialization. This is specialization that's done by the compiler to make the thing. Explicit specialization is specialization that's done by you, the programmer, to make the thing, the specialization. And then we have implicit instantiation, where the compiler sees the usage of a template and does the instantiation for you. We have explicit instantiation, where you decide the time and place where the instantiation is going to occur. And so I will leave it at that. Thank you.